today's topic, there will be no long introduction like yesterday because we've done with that. So I'll get straight to the problem of tanks and anicuts of South India. Now this is the PhD work of Chitra Krishnan, and really my contribution to this is minimal. My biggest contribution really was making sure she didn't quit the PhD midway and join an NGO. Okay, so I sort of kept counseling her till she finished, and other than that, the work is almost entirely hers. There's a little bit of help that I, when we set up the experiments in instrumentation and so on, but really all the legwork in and the intellectual work in designing the experiment is hers. She she did extensive surveys of the Anicut and the region around it. She also located several libraries from which you could get manuscripts describing them, because the records are very few and far between. She also visited the India office in London for some of the details. So she's done a tremendous amount of detective work to put this together, and really it would have been better for her to come and make the presentation. I hope I can do some justice to it and some justice to Professor Danino's kind invitation for this series. Okay. So there are three parts into which this talk is divided. The first is the discussion of the Grand Anicut, or the Kalane. And then this is a side weir, so it sort of divides two streams which are going to join. Okay, it will become clear once I get into the details. The second part will look at a modern weir as opposed to a traditional weir. Now for us, there is a fairly good demarcation between modern and traditional. It is pre-British interference and post-British design and installation. And then the third one, we'll look at a tank system. Now the purpose of the Anicut is to divert water from the river into a canal, and the canal feeds the tank system. Okay. Usually, some tanks are directly tap water from their catchment. Okay, the Grand Anicut, this, as I said, is a side weir, and we'll look at the pictures soon enough. It was built in the 2nd century AD by King Karikal Chola, and it provided irrigation for the Kaveri Delta, about 6 lakh acres or 600,000 acres. And it was really the only structure in that region till actually 1830, till the British started adding structures to the system. Okay. And as I said, the sources for all the material presented here come from the Tamil Nadu archives, the India office in London, and also she was very fortunate to find the personal collection of a farmer family living in Kaveri. Okay, so this is the entire Kaveri basin. The river starts, I guess I should use this. It starts in Karnataka and flows through Tamil Nadu and meets the sea here. Okay, the Grand Anicut is very close to the delta, and there is another dam which we will discuss later on, which is up here, which was built in the 1930s. Okay, so till 1830 or so, this was the only structure that was allowing irrigation in this delta region. The total length, I think, is about 760 kilometers from. Okay, now before we come to the Grand Anicut, there is the Kaveri divides into two streams. Akhand Kaveri means undivided Kaveri, so that's flowing here. And at the island of Srirangam, there is a bifurcation into what is called the Kollidam and the Kaveri. Kollidam literally means region of spill, where Edam is place or region, and Kol is the fall. Okay, so this upper branch is more steep and much faster flowing, and it's not was not being used for irrigation. It just flows directly to the sea. Okay. The lower branch, which is slower and the slope is less, actually feeds the delta, and that is where all the water for irrigating this 600,000 acres comes from. Okay. Now, the two branches bifurcate here, but they join again here in this region, and we'll blow it up a little bit. And the purpose of the Grand Anicut is to prevent the two streams from joining. If they join, then most of the water from the Kaveri would flow into the Kollidam, and there would be very little for irrigation. So that is why it's a side weir. It's preventing two streams from mixing up. On the other hand, there's a second purpose, and that is during floods, it's meant to transport excess water into the Kollidam so it does not destroy the crops and inundate them and destroy the crops. So it has a dual function. When in normal flow, it's meant to prevent the Kaveri from falling into the Kollidam, and so that the Kaveri is available for irrigation. And during flood, it allows excess water to escape into the Kollidam so that the fields are protected. So the design is very crucial. If it's too high, then it won't take care of the flood. If it's too low, then it won't take care of the irrigation. Okay, so there is a little more detailed view. Again, you can see that this is the Grand Anicut, and that's the island of Srirangam. And finally, further blow up shows you where the separation is. This is the Kaveri, and the Ullar is the river that connects the Kaveri to the Kollidam. So during floods, this is the one that is activated to remove the excess water. Okay. We were fortunate enough to get a drawing of the Kaveri as it existed before any changes were made. So you can see this is the plan view, and this is the elevation. You can see the main structure is a masonry structure about 1,000 feet long, so about 350 meters long. Okay. And it's not very high. It's about, at that time, it's about 7 feet high. It's possible that when this was made, the Kaveri had silted up, so the actual height could have been closer to 10 or 10 feet or a little higher. Okay? But at that time, it was around 7 feet high. And if you notice, there is a small slope given to the top. See, at this end, from this end to this end, there's a drop of about 1 foot 4 inches, which works out to a slope of 1 in 900. So it's a very tiny slope, and it's very easy to mistake it for an error in construction rather than assume that it has some purpose. Okay. The other interesting feature is this serpentine plan form. Okay. Then there were, to hold it in place or to keep the rivers from mingling before the Grand Anicut, you have two large embankments, and they are fairly long. One of them is about 1,000 feet, and the other one is about 5 miles. So they're very large embankments. And the final feature is that there is a drop across the Grand Anicut as you go from the Kaveri side to the Ullar side. There is, I think, about a 2 foot drop from this base to that base. And the Anicut also has a sloping top wall. Okay. Now, the story begins in 1800 when the British were informed that there is something wrong with the Kaveri by the king of Tanjavur, who governed the part to the east of the Kaveri, of the Grand Anicut. So it was the kingdom of Tanjavur that was being irrigated by the Kaveri. Okay. Now the problem is like this: the Kaveri was silting up, and the flows were reducing every year, and therefore very little was available for irrigation. Now the reason for the silt load can be taken back to the point of bifurcation. When you have a bifurcation of a stream into two streams, the water and the silt do not move in proportion to each other. And very often the stream that has less water is carrying more silt. Okay. And there are very few measurements available, but there was one which Chitra managed to find of bifurcation on the river Rhine. And here you can see Q1 and Q2 are the flow, water flow measurements, and S1 and S2 are the silt flow. Okay, so what is plotted is S2 by S1 versus Q1 by Q2. So Q1 by Q2 is about 2, a little more than 2. So that means the flow in this is double this. So 60% is going there and 30% is coming here. On the other hand, S2 by S1 is about 1.5. So the stream that's carrying 1/3 of the water is carrying 1.5 times the, or it's carrying 60% of the silt load, 66 or so, or 60%, yeah. And that is the start of the problem, where the Kaveri bifurcated into the Kolidam, and the Akanda Kaveri bifurcated into Kolidam and the Kaveri. At this point here, because of the higher slope, more water was going into the Kolidam, but at the same time, more silt was coming into the Kaveri. Okay. Now, the main reason for this sad state of affairs was I guess, as usual, political. As I said, to the west of the Grand Anicut, you had the Nawab of Arcot, and to the east, you had the king of Tanjore. And I think in the mid 1700s, they did not see eye to eye. So there was no cooperation between the two. Now, the usual arrangement was till, I guess, 1770, that if there were any repairs to be done, then the embankments would use the mud and the materials available from the Nawab of Arcot's territory. But once the things fell out of place, this was not permitted. So their repair work was much more difficult. And in 1776, there was a huge flood, and that breached the embankment on the left side. I don't know whether I have a picture of that. No. Yeah. This embankment was breached in 1776, and because of the political problem, it could not be repaired properly. And after that, slowly, and I think along with that, the Grand Anicut itself was not in good repair. And after 1776, the silting problem started. And by 1800, it was so critical that there was a fear of famine in the Kaveri Delta. That is when the king of Tanjore approached the British. So the first thing, they initially studied the problem and looked at the Grand Anicut and concluded that one, they found that the surface was very rough, and they didn't realize, I guess, at that time that the plaster made with the lime plaster had been eroded because of poor maintenance, and so they felt that the stones are exposed, and some of the stones must have been removed by the water. So, and they concluded that's probably the main reason why the silt is not being transported across, and the flows in the Kaveri are reduced. So they raised the height of the Grand Anicut by about 2 feet. Not only that, they said the slope is irrelevant, and they flattened it completely. The original Anicut structure not only had a gentle slope from upstream to downstream, it also had a few depressions. Again, these were assumed to be just the Grand Anicut in bad repair rather than in serving any purpose. So that also was flattened, and the top was made completely flat. Okay. Now, and but unfortunately, this did not solve the problem. The silting problem kept getting worse, and in 1830, then 2 undersluices were made under the Grand Anicut to allow the silt to escape, so that more area would be available for water to flow into the Kaveri. And when that helped to some extent, and then finally in 1836, there was a dam constructed here in the just downstream of the bifurcation point, so that the flow in the Kolidam could reduce. This happened, it took care of the problem for some time, But then you had the reverse problem. Too much water was then flowing into the Kaveri, and therefore the river bed was getting eroded, and then there was a danger of again flooding the irrigated area. Also during flood, now because the river bed was much lower, the excess water couldn't be transported across the Grand Anicut. So then there was a regulator built on the Kaveri. Then this was, I think, the Kaveri Dam was in 1845. So that took care of that problem. Then later on, to allow the Venar to irrigate more land, the point of attachment of the Venar was shifted from this point to very close to the Grand Anicut. And then later on, regulators were put on the Venar also to control its flooding problem. And finally, in 1934, the Grand Anicut Canal was added here, and another dam was added upstream. The present situation is that I think about 35% of the total water flowing into the Kaveri is being used for irrigation. If we look back at the records and whatever we can make of them, the Grand Anicut, when it was functioning alone, was taking care of about 20% of the water flow that was available, 20% of the runoff. And this is a very rough estimate. But it was serving about 600,000 acres. Now the area covered is much more, but this is the complex system that exists now in the region where the Grand Anicut was. This is the Grand Anicut, which was the only structure before 1830. And now you have the regulator here, you have the Grand Anicut Canal, you have another regulator here, and then you have the dam on the Kollidam, and then the dam much further upstream, the Mettur Dam. Okay. So now it's called no longer called the Grand Anicut, it's called the Grand Anicut Complex. Okay, so now what we were trying to understand is how a single structure more or less performed the function that it was meant to do for almost 2,000 years. It was built in the 2nd century, about maybe 1,600 years, and the problem started in 1800. The overall conclusion is that if the Grand Anicut had been kept in good repair, I don't think there would have been a problem around 1800. I mean, it could have continued without any interference. Okay, the main problem started because the maintenance could not be carried out properly. Now, as I said, the function of the Grand Anicut was twofold. One is to, during normal flow, it was to prevent water from going to the Kollidam. But during the flood, it was meant to transport water. In addition, the excess silt that had accumulated in the Kaveri also could be transported when the flood waters crossed over into the Ular. Okay. Now, to understand how this could have happened, let's look at what happens in a typical river when you have a river flow and a canal offtake. Okay. This is the typical design of a canal from a river. The angle that's here is between 30 and 45. So 30 is a typical value. Now, what happens when the river bifurcates into the canal? It is taking a curved path. Okay. Now, when a fluid stream has to take a curved path, then you need a pressure gradient normal to the curve to allow that. Or, I mean, you can look at it either way. Either the pressure gradient drives the flow, or the curvature of the flow creates the pressure gradient. In any case, you need to have a radial pressure gradient to provide the centripetal acceleration if you're looking at it in inertial frame, or the centrifugal acceleration if you're looking at it in a non-inertial frame. I prefer the inertial frame, so I will stick with that. So you need a pressure gradient that drives the flow towards the center. Okay? So if it's curving this way, there should be a force in this direction, which means the pressure in this part must be higher than here. Now, the pressure gradient is decided by the surface flow, which is moving at the peak speed. And it has to provide the centripetal acceleration, which is v squared by r, where r is the radius of curvature. But when you get to the bottom, the velocity is much reduced. But yet it is subjected to the same pressure gradient, and therefore at the bottom there will be a transverse flow. So it's called a secondary flow. Excuse me. So at the bottom, you will get a secondary flow going this way, and this is what forces the silt to move towards the center of curvature. Okay, and of course, to close the system, the secondary flow sort of goes around in the circular manner. If I look at the velocity in the plane, the actual path taken by a fluid particle would be a spiral. Okay. Now, because of this secondary motion, the bed is eroded in this region and brought to to the upstream side. And one of the major problems this creates is that it brings in dumps silt in this region and very often chokes the canal. So this problem is a very standard problem from the point of view of canal maintenance. And unless this region is kept clear, the canal will become dysfunctional soon. Now, there are several ways to address this problem, and we will look at a couple of the modern solutions, and we'll look at the traditional Anicut, which also takes care of this problem. But what is of importance to us in connection with the discussion of the Grand Anicut is what's called a sand trap, which is used to prevent this erosion and the silt from being transported in the canal. Okay. In the 1950s, Leliavsky was posed with this problem of preventing silt from choking the canal, and he developed this idea of sand screens. Initially, what was done is that they just put a barrier here to prevent silt from going into the canal, but that didn't work too well, because when you put a barrier like that, it creates an upflow, and a lot of the silt is carried with that. Then what Leliavsky did is he realized that because of the erosion, you will get a slope of this kind, right? When the flow is curving this way, then the silt is carried towards the center of curvature, so this part gets eroded. So the bed slope just at the entry to the canal has a positive slope in the downstream direction, or it slopes downward in the downstream direction. And so to counter this, he put a sand trap that has the reverse slope at the top. And this allowed the water to go over without carrying the silt with it. Okay? So this completely fixed the problem of silt going into the canal. The Grand Anicut, on the other hand, has a slope in the direction of in the same direction as the bed, and therefore it was able to transport the silt, which was what it was meant to do. It was supposed to transport silt from the Kaveri into the Ular, so that it would be carried into the Kolidam. And during flood, there is no danger of the Ular silting up, because again the slope is much higher there, and therefore that was a very safe transport problem. Now, so Leliavsky has given some empirical formula to estimate the magnitude of this slope, and if you put in the expected velocities during a flood on the Kaveri, which is the surface velocity is about 2.5 meters per second, and back calculate what the slope should be, it comes out exactly to about 1 in 900. So the Grand Anicut upper slope is exactly the same as the bottom slope, and that's what helps it to transport the silt across and prevent the reduced flows in the Kaveri. And this was the main thing that people did not understand, and that's why they tried to make all the other changes, which I mean, somehow in some manner was sort of got to made to work in about 40 to 50 years. But the secret of the Grand Anicut lies in this slope, and also in the undulating form, which allowed the silt to be kept in suspension, so it could be carried over in the case of a flood. So the that may be secondary. The upper slope, I think, is the primary reason for the silt transport. Okay, so now we'll come to the second part, which is the comparison of modern weirs and traditional Anicuts. The tank and Anicut system is quite extensive in South India. I think one of the estimates puts the number of tanks to about 300,000 or 3 lakhs. And the total irrigated area of about 40 lakh hectares. The sizes are also variable. You can have very, very tiny systems to fairly large systems. The highest in terms of bund height, that is the embankment height, is 30 meters. So it would, in the modern classification, classify as a large dam or a large bund. The tank circumference, the largest one is 64 kilometers. So that's also quite huge. And the largest capacity could be as much as 75 million meter cube. Okay. As I said, one of the problems that you get with a canal is this silting up and reduced function once the entrance is silted up. And there are several ways to handle this problem. One solution, if you're lucky, you find that the place that you need to put the canal happens to lie close to a bend in the river. And then if you put it on the outer curve, then the secondary flow actually pushes the silt away from the canal into the main river. And so the canal is kept free. So this is one method of preventing the canal from silting up. The other one people use is putting submerged veins to prevent the transverse movement of silt. Another solution, again, if you're lucky, if you have an island or around which the flow has to go, then you can, again, you get a similar effect as with this curved river flow, and you can take the canals from here. And of course, the last one is what we had seen earlier. If you design your sand screen properly, you can prevent the canal from silting up. Now, what we found from on the basis of our investigations and the experiments, the traditional Anicut seems to achieve this without any extra device. Okay. Which one? Submerged veins. There are a series of veins which sort of guide the flow, and they will prevent the transverse motion of silt at the bed. So effectively the pressure gradient that's felt is blocked by the vein, and therefore the bed movement is not there. Okay. No, they would actually keep the churn the thing. But what happens with a submerged vein is there will be erosion at the base of the vein, and so you'll have to periodically make sure that that is taken care of. Or maybe you'd have to have a large structure which sort of forms the base, so that around the structure there is no erosion. I mean, anyone standing at the beach and in the midst of wave must have noticed this. The sand around your foot gets eroded and you keep sinking in slowly. So that's what would happen, because there is a vortex created around the structure, and that churns up the silt and then carries it away, so that you start sinking slowly. So that is the problem you might have to face, but otherwise it should be okay. Okay, so this is the thing. In the previous pictures, we just showed the canal, but usually in order to divert the flow into canal, you need a weir. This is not a dam, it does not obstruct the main flow, it only creates a resistance, so some of the flow is diverted into the canal. If this were not there, there's no reason for large flow to enter the canal. Most of the flow would go into the main river. So to ensure that there's enough resistance in the main river to divert the flow, you need a weir. And this is the standard modern weir. It is a flat top and straight across the river. Okay. The traditional Anicut or weir is actually more complicated. It starts off perpendicular to the river and then goes at an angle, and towards the end it's almost parallel, and the canal starts off almost parallel to the river and then diverts and then diverges. Okay. And very often there are one or maybe even two depressions, one usually in the center and one near the tail. This tail depression would allow some of the flow to come back into the main river, and this might help in preventing sediment from going to the canal. Okay. So this is we wanted to compare these two systems. So here we decided that we will set up an experiment and try and mimic what happens in a river. And so this is our river. It's about 4 meters long and 1 meter wide. And then there's a provision for having a canal at 30 degrees. This served two functions. It allowed us to test what happens when we put a modern weir across here and look at the flow into the canal. It also allowed us to put a side weir and look at, in some way, what happens when you have a structure like the Grand Anicut. Okay, that experiment was not that conclusive, but the other experiments were fairly useful in understanding or in explaining what's going on. Okay, now the entire thing, as I said, is the useful region is about 3.6 meters. The width is 1 meter, and you had an inlet tank and a small converging entry to make sure that the flow is uniform. Okay, and you had two outlet tanks. The outlet tanks were provided with screens so that we could measure the flow of water and measure the flow of silt or sand that we introduced into the main flow. Okay, and then the waters, the sand, if you introduce sand, then that is separated here in these tanks, and then water is again pumped back to complete the system. Okay, so there were a couple of issues with this modeling. We did both experiments with a fixed bed, and there were two types of fixed bed. One is just a smooth bottom surface. The material here, this tank was made of perspex or acrylic sheets. So in some of the experiments, we just had a plain acrylic sheet. In some others, we glued on a thin layer of a 2 mm layer of sand on it, so that we simulated the roughness of the river. And in the most sort of complex experiments, we actually put in a 2 centimeter layer of sand and allowed the sand to be moved by the flow. So you had a mobile bed, and so dunes would be formed, and that would affect. Then you could look at what happens to the flow and what happens to the silt and so on in the different configurations. We also looked at some way of, investigated a little bit the effect of slots on the traditional anicuts. Okay, the experiments had several parts. Initially, we looked at we tried to visualize the flow, look at what happens to the flow at the top surface and at the bottom surface to see, to get an idea of what the transverse currents are like. Okay. So to separate these two, we had a rake of, I think, 5 pairs of needles, one which allowed dye to be injected towards the upper surface of the flow and one near the bottom of the flow. For the upper surface, we used potassium permanganate, so that's pink in color, and for the bottom surface, we used greening. Okay. Then, if we go back, the setup had 2 rails on either side on which we could mount a traverse and move our probes and our dye injection system and so on. We needed to measure, one is the flow rate coming out from these 2 branches, the main river flow and the canal flow. We need to measure the surface undulations or the surface levels to see, to have some idea what would happen in case of a flood. Okay. We also needed to measure the flow velocities at different points. So the instrumentation is based on that. Okay. So to measure the surface, we could traverse a depth gauge using the rails in both directions. Oh, yes, I should mention. This is our origin, and y is this coordinate going transverse to the flow, and x is in the direction of the flow. So we could measure at different x and y locations over this surface. Okay. Now, of course, once our traverse is not so high tech. So we were doing it on a fairly low budget. So what Chitra did was initially just filled up the tank, and then you know that the water surface is perfectly flat. And then she used a depth probe and got the 0 readings, which were variable because of the small manufacturing defects in the rails, in the longitudinal rail and the transverse rail. And so she had a base measurement for a clean surface. And so all the later measurements of the surface height were compensated for the error in the base measurement. Okay. Then to measure the velocity, there were two methods. When the velocity is very low, we had to use an optical method. We just had a video camera, and she overlay a grid on top of the flow, and then she could look at what happened to the dye streaks as they went through that grid. For higher speeds above 25 centimeters per second, we use a 2-hole offset. It has, it is just a bent probe with one face upstream and the other face downstream, and so you can measure the pressure difference between the two and estimate the velocity. And there, since the deflections are very small, we had a traveling microscope to tell us the difference between the two levels, and we were able to get about 0.5% accuracy at 25 centimeters per second, and the accuracy improves once the speed is higher. And finally, for the mobile bed experiments, we need to supply sand at the same rate at which it's being transported downstream. So we had a conveyor belt and a hopper. This was the most tricky part of the experiment because getting a uniform layer of sand continuously being fed into the flow and trying to adjust the system so that the inflow balanced the outflow took a very long time. So the typical mobile bed experiments went on for about 60 hours, which means someone had to, Chitra had to spend 2 nights without sleep and continuously monitor the experiment. Okay. As I said, I was fortunate that she had the tenacity to do it. Of course, it helped that she chose the problem, so she couldn't give up midway. All right. Now, what we're trying to do is model a river, and for this particular experiment, the Anicut that we chose were on the Tambraparni river. So the shape was more or less a sort of cartoon of the Anicut that exists on that river, and that is about 200 meters wide, and we are bringing it down to 1 meter. So the scale is 1:200. But if you do the same thing, if you sort of do a careful analysis, which I will not have the time to get into here, and find out all the non-dimensional parameters that govern the flow, you try and match as many as you can, you find that the depth of flow is about 5 millimeters, and which is very difficult to do any measurements in. So we allowed for about vertical distortion about 5 or 7. So we got a depth of flow about 3 centimeters, so that we could distinguish the surface flow from the bottom flow. There are some issues in doing that, but the 2 critical parameters that you need to match are the Froude number and the roughness coefficient. The third one, if you distort the flow, then you can get by changing the slope slightly. So what we ended up doing is increasing the slope by a factor of 4 from what exists in the Tambraparni, so that we could go to a higher depth. Okay? But it's still not perfect. The Reynolds number you definitely cannot match, but we are fortunate that if the Reynolds number is above 1,000, you can more or less get a reasonable capture of the basic physics. Okay. Now, the first thing she did was with the fixed bed. This is without any flow, without any movement of sand at the bottom. And if you compare what happens to the flow going into the canal with the 2 different configurations, the modern weir and the traditional Anicut, this is what it looks like. Okay. So the as you increase the flow, if the flow is very small, then a lot of it is diverted into the canal, obviously, because it does not go over the obstruction. Okay. But what is interesting is that in the region of low flow, the traditional Anicut is higher, but in the region of high flow, the traditional Anicut actually is lower. Now, this is very useful from a practical viewpoint. When the river flow is low, you want more water for irrigation, and you prefer to have a higher flow into the canal. On the other hand, during a flood, you don't want too much water to be diverted into the canal, because then it will damage your crops. So the difference is not very much, but it is in the right direction. Okay. But again, before we got into the mobile bed, if you look at the streamlines, then you get a more dramatic picture. So in these flow visualizations, you can see the grid that was used to measure the low flow, low velocity situations. The pink lines are what is happening at the upper surface of the water, and the green lines are what's happening at the bottom. Now, you can see that there are 4 lines shown here. The canal is here, all right? So there is, and this is the weir across the simulation of the modern weir. It's just a block of wood of the right, I think 6 centimeters high, placed across the channel. Now, it's only the last pair of streamlines that's actually entering the canal. However, the flow is diverging between the surface and the bottom all the way up to here. Almost a third of the flow is contributing to the bed flow, okay? Which means a large amount of silt from here is potentially being capable of potentially entering the canal. Okay? And you can see that the divergence between the upper line and the lower line gets worse as we go closer to the canal. And of course, when you get very close, again they come close together. On the other hand, with the traditional Anicut, you can see that the difference between the upper flow and the bottom flow is very, very small. And in almost all cases, they are going parallel to each other. So that means the transverse flow at the bed is being prevented by the shape of the Anicut. Okay. What happens really is that rather than a curved flow, you get a convergence in this region because of the shape of the Anicut. So the flow converges here and it actually accelerates through, and that prevents this transverse movement near the bed. Okay. And that is seen here from the surface levels. So these are the surface levels for the modern Anicut, modern weir. Or what is shown is the surface level up to the location of the weir. Okay. And the locations are y equal to 5, y equal to 50, which is the center, and y equal to 95, which is the edge away from the canal. Okay. 5 is entering the canal and 95 is away from the canal. All 3 of them are more or less at the same level. In the traditional Anicut, you can measure through the canal, of course, because we have taken it parallel. You can see that once it approaches the canal, I think the Anicut extends till about 250. So after this, the canal is straight. But there's a tremendous drop in the surface. Okay? That is because the flow is accelerating, and so the velocity is increasing considerably, and then the level is falling down from continuity. Right? Okay, so that is what we did with the fixed bed. It gives us a sort of clue to what is going on, but really a river doesn't have a fixed bed. So the main conclusion should be made from our experiments on the mobile bed. Okay. Okay, as I said, one of the trickiest things was the sand feeding mechanism. After trying several configurations, what we found worked best was to have a conveyor belt on which we loaded the sand and have a scraper at the end, which allowed a sort of controlled amount of sand to enter the flow at the upstream end, and then we continuously monitored it till we were able to match the input and the output, and after that the experiment started. So what I will look at, I think, mainly are these three configurations to get an idea of the time scales and when things reached a stable value. One experiment was done with just a plain bed, or without any weir or anicut, just a plain river. And then one experiment was done with the modern weir and one with the traditional weir. Because of the amount of effort going into this, we could only afford to do one set of measurements of one flow rate for each of these. Okay. The main result, I mean, Chitra measured the velocities, the surface configuration, all that. If someone is interested, that will be in her thesis. But the main result is what we want to address in a practical situation. That is, or what we want to answer in the practical situation is how much flow is going into the canal and how much silt is being carried with the flow. Okay, and for the flow rate that we chose, 26% of the input flow went into the canal with the modern weir, but it carried 80% of the silt. Okay. On the other hand, the traditional anicut had a smaller flow, but it only carried 50% of the silt. Okay. So that is one part of the story. So if you look at the numbers, I mean, the ratio between 50 and 18 is slightly smaller than 80 and 26. Okay. But carrying 80% is not very healthy because it will soon choke up the canal. Now, if you look at the final bed after the experiment went to close to steady state, you can see that, as expected, with the weir and modern weir and the canal offtake at 30 degrees, there is a scour region here. You can see that a lot of the sand is eroded here. There are another picture which unfortunately I don't have in a soft copy, which shows that there is a lot of buildup of sand in this region, and there is a buildup in this region also. Okay. On the other hand, with the traditional anicut, the entire entry to the canal is scoured, so it's kept clean, and there is no buildup downstream also. Okay, so most of this thing has been transported across, and it is carried with the main flow. This is another close-up of the scour region with the modern anicut. You can see this here. One way to explain this bed movement, the secondary flow is useful. If you want to understand why this part is eroding, what I said earlier, when you have a fixed post in a moving flow, then there will be a vortex that lifts up the silt and carries it down. That explains this erosion. Okay, and if you look at the water surface levels, then the picture is a little more dramatic. You can see that there is a considerable difference in the surface levels between the modern weir and the anicut, and this is extremely useful from the point of view of flood control. Okay, so the overall picture is that the water level in the modern weir is higher, in the traditional it's lower. The surface velocity goes the other way around, obviously. So the velocities are much higher with the traditional anicut, but this is very, very useful in a flood situation. Then this I have not shown you, but you could see a transverse slope in the bed with the modern weir, and the transverse slope was negligible upstream of the Anicut with the traditional Anicut, upstream of the canal. Okay. And then again, the Scour is in the modern system is at the downstream end, and here the Scour is right across. So the entry to the canal is always kept open. Okay, I think I will skip this and then go to the. This is the side weir, and I'll just get on to the tank system. Okay. Have about 10 minutes? Yeah, more than that. Okay. Okay. I think I'll take about 10, 15. So this is the last system we looked at, which is the entire tank system on one of the rivers. And I should, who was the student who made the short presentation yesterday? I have to apologize to you because you're right, it is in Karnataka, not Tamil Nadu. The system that the Pala river flows from Karnataka to Tamil Nadu, and this system is in the upper reaches, so it happens to be in Karnataka, not in Tamil Nadu. So I'm sorry about that. Okay, so I think on this river there are several thousand tanks, and we try to identify one set where we could sort of investigate in some detail, and the smallest set that we could find was about 198 interconnected tanks. So there's about 200 tanks, and this is how it looks on the topo sheet. Okay, this is how the tanks are placed and how they are connected. There is a huge variability in the size and catchment and so on, and there's also large difference in the age. I think the oldest tank would be around 1,000 years old, and the newest is about 200 or 250 years old. So just to give you an idea of the variability, as I said, it's about 200 tanks covering about 550 square kilometers. The capacity of the largest is about 5.7 million meter cube. The smallest is 0.007 million meter cube. So it's about 800. The difference in size is a factor of 800. The catchment area can vary from about 6,400 to 32. The area irrigated again is in the ratio of 1 is to almost 850. Then some of the tanks have no other tanks connected to them. Those are what is at the tail end of all these, at the tail end of the system. You can see this tank has no input, it has an output to the next tank. And some of the large tanks had as many as 11 feeders coming in as overflow from smaller tanks. And again, the large tanks were so big that they could not be filled up by their catchment water alone. They had to get input from the smaller tanks to fill up. And a lot of the small tanks held only about 30% of their catchment. Okay. The difference in altitude, the highest tank was about 900 meters above sea level, and the smallest was, the lowest was 800 meters below sea level. The other interesting thing is that the total storage was about 47 million meter cube, which is about 11% of the total runoff expected, or total, sorry, not runoff, the total rainfall expected in that region yearly. But the biggest 11 held about 60% of the capacity, and the other 187 held the remaining 40%. Okay. Now, we try to look at these numbers in several ways to see why they should be such a huge variation. That is one thing that we sort of can explain if we divide it into two classes, large tanks and small tanks. We seem to understand partly why that is required, but the rest of the variation and the method in which one would add a tank to the system, that I'm afraid we have absolutely no clue. I mean, I've looked at these big maps and figures. Maybe at some probably one of the things on my bucket list. I should spend a few months trekking in the hills. Maybe something will strike me. But I've looked at these maps for over 10 years now, and I still don't understand how one would go about adding to the system without interfering with what already exists. But obviously, that knowledge existed because things were added over almost 800 years. Okay, so we thought it would help if we converted that topo sheet into this, but it didn't really help. Okay. So Chitra spent a lot of time preparing this map and tried to make the area proportional to the size of the tank and so on, but it didn't help too much. What she did was try to get rainfall records for the region, and also did some amount of field work in that region. What she found is that the rainfall is very, very variable. It gets fed by both the southwest monsoon and the northeast monsoon rains, but it is very variable both spatially and temporally. So some of these 198 tanks, it's not a very large area. Some of them could have very heavy rain, some of them would have no rain at all in the same monsoon event. Okay. And most of the rains were not sufficiently intense to give runoff into the tanks. And what she measured in one of the places was that it was varied between 4 and 6% for one particular tank, while the data given in the tank register, which the British maintained, estimated it to be between 12 and 15%. Okay, we are not sure whether the problem is because the catchment area has been changed. I mean, there must definitely have been a lot of deforestation in that area, change in land use, etc., which is what led to the much lower runoff, or whether the tank register inflated the number slightly because taxation was based on the revenue, or the taxation was based on the expected income from the irrigated fields. The other thing she did was to look at the local soil and try and estimate what would be the silt load into these tanks. A lot of the tanks are in very poor state of repair. More than 50% of the volume is silted up. And there's been no maintenance, I think, for more than 100 years, or yeah, probably 100 years now. But what she was able to deduce is that if people were regularly maintaining the system, then it is not too hard. She looked at 3 different tanks and looked at the expected silt load into them, and that gives you the volume of silt going in there. And she estimated that if even without modern trucks and excavators, if you used the means available to someone about 200 years ago, just a bullock cart and human labor, then to desilt these tanks, if you look at the numbers, these are 3 of the largest tanks. You would require about 60 to 150 human beings working for 1 month to take care of the annual maintenance. Okay, and if there's no maintenance, then about 10% of the capacity would be lost for this tank number 405 in 20 years, and for the largest tank, it would take 80 years to lose 10% of the capacity. Okay. Okay. So the sort of piecing all this together, what she concluded is that the reason for this large variability in sizes, which is, I think, the main question in the discussion yesterday, is that the given the variability in the rainfall and the variability in the runoff, the large tanks do not fill up every year. You can at best expect them to fill up once in 3-4 years. While the small tanks, because they don't really have the capacity to hold all the catchment water, they fill up every year. And but since the capacity is small, they are good only for one crop. which is the crop of rice immediately after the monsoon. While the larger tanks allowed you to have a second crop in the summer, and I don't know the exact reason. Apparently, the summer crop is much more productive, and it yields almost double the amount of rice per acre compared to the monsoon crop. And therefore, the system was designed that every year you get some produce, but every 4 years you get a bumper produce where the large tanks also contribute to the second crop. So this combination optimizes the system given the variability in the rainfall, both spatially and temporally. And she did some rough numbers and found that the amount of rice produced by that could be produced in principle by that region could support a population of about 150 persons per square kilometer. And if you look at the 1981 census, then in 1981 there were about 180 people per square kilometer in that region. So maybe till about 1950 or 1920, definitely the system could have been self-sufficient. Of course, this is only looking at rice. With the rice requires a large amount of water. You could also have other crops like ragi or millets grown with much less water, and that definitely was being used to supplement the rice crop. Okay, so these are the main conclusions. I think I've gone through all these points, so I'll just let you read them. Okay, and thank you.